So for the people who are researching this field of quantum gravity or making quantum mechanics coherent with general relativity, what advice do you have for them? For people who are going into this field, for young people as well, just entering math and physics, for people who are going into specifically what you study, and for people who are researching?
Right. I mean, so I think I guess the one thing I would say is that I feel like the landscape of gravity research, for example, is quite a difficult terrain at the moment, in the sense that if you're a student and you want to study, say, quantum gravity or reconciling gravity with quantum theory, there's very few games in town. You know, if you're a graduate student, for example, you can work in the string theory group or a loop quantum gravity group. There's a few of those, although that's a much smaller field. And then there's a few of these kind of individual programs, which maybe involve just, say, a couple, 3 or 4 researchers. And it's a very difficult terrain as a student because, you know, the history of physics is that usually it's young people that make, you know, new paradigm shifts or great physics discoveries. And I feel like it's difficult these days to work on your own stuff. You almost, there's this, because there are these big communities, you're almost like pushed to attach yourself to one of them and become a string theorist or become a loop quantum gravity person. And I think that is unfortunate. And I think what we really need is people to kind of go off in their own direction and do their own stuff. And I think that, you know, invariably will mean attaching yourself to some group, but hopefully being given the freedom to, you know, go in a different direction. And I think that's, you know, I think that's the sort of, you know, the questions you need to ask when you're starting on a research project is, you know, how much scope do you have to do your own thing? Or can you find, you know, if you really, I guess, have to find something you're really interested in and maybe a supervisor who has the same interest, or you have to somehow go off on your own. And that's a lot harder. And I fear that that is one of the reasons that it's so difficult to make progress in quantum gravity is part because it's a really hard problem, but in part it's because there's not a large scope for just going off on your own. You are often just, you know, in some sense drafted into an existing program.
When you say that there's not a large scope, you mean there's not funding or there's not opportunities? Well, opportunities equals funding.
Well, it's hard to know exactly. You know, it's a multifaceted problem. I think part of it is that, for whatever reason, people like to work on the same thing as everyone else. And I mean, we are social creatures and we want to be part of a community. And so if there's a big community doing something, then it's very natural to want to be part of that community and do that research. But I feel like it's gotten to quite an extreme, it feels quite extreme at the moment. I feel like even when I was a student, you know, there were various researchers who I would say didn't have a firm allegiance to, say, string theory or loop quantum gravity, and you could kind of work with one of them and work on your own approach. Whereas I think now, for whatever reason, the landscape has just become a lot more divided into different communities who do different things, and it's much harder to go off on your own. And maybe that's just because students worry that if they go off on their own, they won't get a job. I think that's probably a big part of it.
Speaking of being a student, my brother was a student, a graduate student, or maybe a PhD student at the same time you were studying physics.
That's right. Yeah.
You remember Sebastian?
Of course I do. Yeah. He was, he was brilliant. So, I think we may have even have shared an office for a while. He was, I think, working with Gordon Seminoff. Is that right?
Yes. Right.
Right. Yeah. Do say hello to him for me.
Yeah, I will. Do you have any teachers that have changed your life or gave you a new perspective, ones that are particularly memorable to you, whether in high school or even in university?
Yeah, I mean, in
But not your supervisor, because that's obviously...
That's obvious. Yeah. It's like your father, isn't it?
Yes.
I mean, in high school, I had, I think, a great science teacher, Ping Lai, and he had a PhD in physics, and I think I learned special relativity from him, and he just gave us a lot of scope to kind of explore and think about our own things, and so that was definitely important that I think I had him as a physicist, as a physics teacher in high school, and in elementary school as well. I had a really good. It wasn't even my science teacher, but it was just a teacher that let you just kind of go off on your own and study whatever you wanted. And I feel like that, letting me and letting other students just do whatever go off on your own and study what you want is, I think, a really important part of learning. And for me, obviously, is being able to, I'm fortunate enough that kind of way of learning has been able to continue into, my middle age. So that's quite lucky, but I'm definitely grateful that I had teachers who let me do that at a young age.
And before I let you go, I'm curious, what has been the reception since your Quanta article from the public and then from the physics community?
Actually, I have to say that the people have been quite open to it. I feel like there's definitely been, especially from the relativist community. Well, I would say even from string theorists, I feel like there's been an openness. Often it's of the form of, well, I don't believe that gravity is classical, but I'm glad that you're, exploring the consequences of that. I'm glad someone is doing that. So that's I feel like that's at one end, and so there haven't been many people who most people have been, I think, quite engaged with it. For me, what is the most exciting engagement I've had is there's this community of people who are interested in actually performing the experiment. And so that has been exciting in the sense of, I think what we're going to see is a large scale effort to test the quantum nature of gravity. Because I think for a while, there was always this assumption that in order to test quantum gravity, we needed to go to the Planck scale. We needed to go to incredibly high energies before we could ever make a prediction about gravity. And what we're learning now is that actually there's all kinds of things that you can test for in terms of a quantum theory of gravity, which do not require Planck energies. So, for example, testing whether gravitons can create entanglement, that's something that that doesn't require Planck energies, and which we hope is maybe feasible within the next decade or so. So I think that's been the most exciting, this kind of experimental effort.
If you enjoyed this TOE clipping, then the full video is linked in the description. You should also sign up for TOE Mail, which is again in the description and the pinned comment. You'll receive immediate access to all exclusive updates from the Theories of Everything podcast. It also helps me communicate directly with the core TOE community. You'll also receive my top 10 TOEs. Think of it as the intellectual version of Quentin Tarantino's Obsession.